Hello everyone, my name is Sean and I am from the Nanyang Technological University in Singapore. Today, I will be presenting to you the wonders of motion simulators and how they bluff your body senses. How many of you have ever dreamt of experiencing what your favorite movie scene felt like in real life? Maybe you would like to partake in the exhilarating space battles in Star Wars like the video on the left. Or maybe you would like to experience the thrills of speeding through the dense jungles in a jeep while being chased by a Tyrannosaurus just like in Jurassic Park. Well, I hope you do, because today I will be bringing you all on a journey on how technology can make this happen. First and foremost, I believe everyone recognizes what this device is. Yes, this is a virtual reality headset. Virtual reality, or VR in short, is a computer-generated environment that allows users to experience scenes as if it appears to be real. VR is a form of visual simulator, and depending on the application, could be coupled with audio to make the scenes more realistic. In recent years, VR has becoming increasingly popular, with many new games popping out each year. A couple of years back, I got the chance to play some games on an Oculus Rift, a popular VR headset. One notable game I remember playing was a roller coaster simulator, where you get to experience what it is like to be on a roller coaster. However, as you can probably guess, the experience just wasn't the same. Even though the visuals seemed to be reasonably realistic, there was no thrill at all when it came to the sharp drops or the loops. And that is simply because the body remains still throughout the ride. In that case, how do we create a more realistic simulation experience? You might have already guessed, and that is to introduce a motion simulator. How many of you know what motion simulators are? In a simple sense, the goal of motion simulators is to replicate the feeling of motion into the real environment. The motion involves many variables, including the change in a body's position, orientation, and acceleration. To understand the mechanics behind this machine, let us watch a couple of clips. This is a cable-driven motion simulator, and as you can see, the platform is suspended in the air by 8 extremely strong cables. On to the next clip. This is a very interesting motion simulator. It is basically using a robotic arm. As you can see, the cabin is situated at the end of the arm. So, can you tell the similarities and differences between these two motion simulators? The two main similarities in these two simulators are their motion capabilities in 6 degrees of freedom. Degrees of freedom of a mechanical system is defined as the minimum number of independent parameters required to describe its configuration completely. Or in other words, their ability to move in space. These motions can be classified into translation and rotation, and further segmented into roll, pitch, and yaw for rotation, and surge, sway, and heave for translation. In engineering, when designing a mechanical system such as motion simulators, it is crucial that we consider the number of degrees of freedom that the system possesses. Let us now look at the biggest difference between the two simulators we saw earlier. In the first clip, we saw the cable-driven motion simulator. In robotics, they are known as parallel manipulators, which involve several actuated links, or in the earlier case, cables, that support a movable platform. As for the second clip, we saw the giant robotic arm. They are known as SEAR manipulators. They are designed as a series of links connected by actuated joints. As you can see on the screen, there are more examples of parallel and SEAR manipulators. There are pros and cons between the two designs. For example, SEAR manipulators have lesser load-bearing capabilities due to its cantilever structure, while parallel manipulators tend to be more complex due to having to move every actuator synchronously to achieve a certain position. Every revolutionary product or technology, including motion simulators, has its own origin. Throughout the years, many people have developed, tested, and improved upon this technology. And now, we will be looking at some of the notable breakthroughs that have contributed to shape the modern day motion simulators that we have today. So, firstly, the year 1910 was an important year for motion simulators, as it marked the first flight simulator to be ever created. Known as the Sender's teacher, it was created to teach the art of flying without leaving the ground. But what is it actually? The Sender's teacher was made up of a model aircraft held to the ground by a universal joint and had to be placed in an exposed location with strong wind. The machine was controlled by ailerons and rudder pedals, and was capable of motions in 3 degrees of freedom, namely pitch, roll, and yaw. However, despite the realism of piloting something similar to an actual aircraft, the project was deemed unreliable due to the irregular nature of the wind. Fast forward 2 decades later, we arrive in the year 1929. This was the year Edwin Albert Link created and commercialized the Link Trainer, advancing motion simulator technology and a pioneer to the now multi-billion-dollar motion simulator industry. The machine had organ-type bellows under the simulation cockpit, which inflated and deflated to simulate motion. Similar to the Sender's teacher, it too was capable of 3 degrees of freedom. The Link Trainer was originally created out of the need for a safe way to teach new pilots how to fly by flight instruments. This machine was later renamed as the Blue Box and mass-produced during World War II. And guess what? Over the course of service, more than 500,000 US pilots were trained on these Link simulators. Over 3 decades later, we arrive at a significant juncture in history for motion simulators, which was the creation of the Steward platform, a design commonly seen in modern-day motion simulators. The Steward platform is a parallel manipulator that uses 6 prismatic actuators to control a top plate and was capable of motion in 6 degrees of freedom. This design was publicized in a 1965 paper by D. Stewart to the UK Institution of Mechanical Engineers. Now that you know a brief history of motion simulators, let us look at some of the notable applications of motion simulators in today's world and their impact on society. I've categorized the applications into 3 groups, namely virtual training, research, and entertainment. In recent years, there have been an increase in demand for virtual training, especially the aviation industry. Many airlines, including Singapore Airlines, have their very own flight simulator within their training center. These simulations allow pilot trainees to familiarize themselves with flight controls and react to potential scenarios such as an emergency landing or dealing with turbulence, without having to be on an actual plane. Well, why is this important? According to Boeing's annual statistics on flight accidents, loss of control in flight has become one of the primary causes of fatal commercial aviation incidents, making up almost 40% of total fatalities. With better training, major incidents can be avoided and more lives can be saved. Therefore, wouldn't you agree that pilots should adequately train on flight simulators and gain enough confidence before piloting a real aircraft? Motion simulators have also been used in research and testing of equipment. A good example would be the Challenging Environment Assessment Laboratory developed by the Toronto Rehabilitation Institute in Canada. Integrating knowledge from flight simulators, the institute applied this technology to create an environment to study human balance and locomotive behavior. One of the more notable applications of this simulation was the study of falls for people with disabilities and the elderly, focusing on simulating falls in a safe and controlled manner. Studies such as these are extremely relevant to countries like Singapore. Why is it so? Well, Singapore is one of the most rapidly aging societies in Asia, along with Japan. Did you know that as of 2020, the residents aged 65 years and above made up 15.2% of the total resident population? Yeah. According to the Health Promotion Board, falls are a leading cause of injury among older adults in Singapore. Statistics show that 1 in 3 adults above the age of 65 falls once a year. And this number is set to increase as the years go by, with an increasing proportion of elderly in our society. In this context, the use of motion simulators allow us to better understand falls and enables us to create new technology to prevent these incidents. Lastly, motion simulators have also been used largely for entertainment purposes, including amusement park rides, arcade games, and home-based racing simulators. One example is a ride known as Star Tours, located in Disneyland, as you can see on the bottom right. This uses a modified military flight simulator to simulate a flight through outer space. There have also been a growing community of people creating their very own home-based racing simulators. In recent years, the demand for entertainment has been growing at an astronomical rate. And hear me out. According to a report published by Research Dive, the global gaming simulation market is worth more than $13 billion and is projected to grow annually by more than 17% over the next 5 years, beating even large industries such as the global airlines market. Coupled with travel restrictions caused by COVID-19, an increasing number of people were willing to spend more money on home entertainment. In Singapore, it was discovered that consumer spending on home entertainment increased by 21% in 2020 alone. This presents many opportunities for the development of motion simulators for entertainment purposes. Who knows, maybe one day we will all have our very own motion cinema at home. Now, after hearing about the wonders of motion simulator technology, have you wondered how our bodies feel the sensations of motion? The way we perceive our surroundings is through the various sensory systems in our body, such as the sight, hearing, and touch. These sensors are known as receptors, which translate stimuli into sensory signals and transmit them to the brain. For example, light entering our eyes or sound pressure stimulating our ears provide us with sight and hearing respectively. In the case of motion, our body perceives its position through 3 classes of sensory inputs: proprioceptor, the vestibular system, and visual inputs. Firstly, proprioceptors are receptors located in your muscles, tendons, and joints, which send signals to the brain regarding the body's position. Proprioceptors respond to stimuli generated by muscle movement and muscle tension. These sensors present a picture to your brain as to where you are in space and the external acceleration forces on your body. To give an example, I believe that all of you have rode on a plane before. The moment before the plane takes off, the plane rapidly accelerates from rest. Do you remember feeling yourself being pushed back into your seat during this process? What actually happens is the proprioceptors within your back and pelvis transmitting this experience to the brain. The brain interprets this information as a forward acceleration. Now, in the event of a sudden braking, such as after the plane touches down, you feel as if you are being pushed forward and away from your seat. This is the proprioceptors on your hands, feet, and rear doing work to try to slide forward in the seat. In turn, the brain now signals the muscles in your arms and legs to contract to stop you from sliding forward in the seat. Next, the vestibular system is the balancing system of the body and is contained in the inner ear. It consists of 3 semicircular canals or tubes arranged at right angles to one another. We can define space using 3 planes perpendicular to each other: the longitudinal axis, which allows us to move forward or backward, the lateral axis, which for left and right motion, and lastly the vertical axis, which allows us to move up and down. Each canal is assigned to detect motion in each plane. When acceleration takes place in a particular direction, fluids within the appropriate canal are displaced, which in turn causes hair follicles to move. The movement of the hair is interpreted by the brain as an acceleration. Also, rotation in the roll, pitch, and yaw axis are indicated by the motion of fluids within the canal. Lastly, did you know that our eyes are also important sources of information regarding motion? The eyes present pictures of the body's position and velocity relative to the ground to our brain. For example, if you are in a car turning left, you should see the scenery displayed in front of you also shifting to the left. Simultaneously, you must also feel yourself through the body's proprioceptors and vestibular system turn to the left. If this doesn't occur in real time, then you might probably experience motion sickness and become disoriented. So, what does the future hold for motion simulators? Personally, I believe that there is a lot of potential for motion simulators to be applied in the daily lives of people. For instance, motion simulators can be used to support hospitals and rehabilitation centers by creating an avenue for people with disabilities, such as children with cerebral palsy, patients with spinal cord injuries, or neuromuscular diseases. And this allows them to enjoy similar experiences to able-bodied people, such as driving a car or flying a plane. Another industry that could potentially benefit from this technology is the sports industry. In the recent 2020 Tokyo Olympics, one notable event for Singapore was sailing. During one of the women's events, two of our sailors managed to clinch the first position in one of the qualifying races. The duo made history as the first Singaporean sailors to earn a place in the medal race at the Olympics. This emphasizes the importance of providing more support for our athletes so that they have a better chance of achieving greater heights in future competitions. For engineering, contributions can be made through the development of technology that can boost the capabilities of our athletes. How do motion simulators come into the picture? Well, if we are able to incorporate them into sports such as sailing, athletes will be able to train without having to be on water all the time. Water conditions can also be replicated to provide them with a realistic training for overseas competitions. It is also easier for the strength, structure, and skill of the athletes to be assessed on land. With all that said, technology plays an important role in society today, and it is imperative that we, as engineers of the future, oversee the creation of technology that could potentially impact lives positively. Before I end off my presentation, I would like to leave behind a quote by Bill Nye. There's nothing I believe in more strongly than getting young people interested in science and engineering for a better tomorrow for all humankind. With that, I end my presentation. Thank you.